Class starts at 10:50, right? Welcome back to class. Last time in class, we talked about several different things. We talked about compounds versus atoms, or compounds versus molecules, atoms, I did it again. Elements versus compounds, molecules versus atoms. There you go. I just don't think of them that way. And we talked about a few other things as well. Do you guys have questions about anything we've talked about so far? Everyone feeling okay with the material so far? You willing to say at this point? Yeah.
Can you kind of like visually show us like atoms versus molecules and then elements versus compounds?
Sure.
Homogeneous versus heterogeneous?
Well, maybe. Well, no. So when you're looking at the various levels of things, start with homogeneous, heterogeneous. Homogeneous looks the same. Okay, so like if I was to draw a picture of it visually, it'd look the same. Okay, so this would be a homogeneous mixture here. Okay, because you're seeing it. Now, if we were to zoom way in with like a microscope or something, you could actually see differences, but in terms of your naked eye, you don't see anything at all. Okay? A heterogeneous, on the other hand, is going to have pockets of other stuff mixed in. Like this. So when you're looking at it, you're going to see different things. Does that make sense for those two? When we're talking about atoms and compounds, or atoms and molecules, and elements and compounds, here, say for example, we've got iron. That is just an atom. Or we could have chlorine as an atom in and of itself. Just one unit of one thing. Okay? And that thing is something on the periodic table. The most basic level of materials is all in the periodic table, so we go to that level. Compounds, on the other hand, or their smallest unit is a molecule. This is when you have two or more atoms stuck together. So iron oxide. Okay, so where we have atoms that are bound to another one. So think of it as whenever you have atoms stuck together, that is a molecule. Is the smallest unit of an atom's is the smallest amount of an element. So whenever you have just one atom all by itself, that's an atom, and that represents an element. When you've got them bound together, stuck together chemically, that's when atoms are going to become molecules. Does that kind of answer your question okay? I know oftentimes when I'm up here talking about things and using words and stuff, it's hard to, if you're not familiar with the word, you get kind of tripped up on stuff. So keep asking me for pictures and things. I think a lot of students find that very useful as we're going through it. Now, granted, my drawing skills are not great. Later on, maybe I'll draw a hand at some point in the semester, and everyone laughs at my hands. It's hard to draw a hand. I don't know. But anyway, I'll do my best. Any other questions about this before I erase the board or move on a little bit? Okay, then the next thing what I want to do today is get one of our attendance things out of the way. So if you would, take out a piece of paper, rip it in half, rip it in a quarter, rip it into 16th, I don't care. You have to write basically your name on it and then answer the question. Share the paper with your neighbors. There's no reason to waste paper or whatever. Yeah, there is. Okay, so the first thing you want to do on the piece of paper is write your name. Obviously, if you don't put your name, you're not going to get any credit. Now remember, none of you are going to lose points because you're here for attendance. So you're all good as far as that is concerned. So basically, you're going for the extra credit points at this point. And the question I was going to ask today is this. What is the difference between a chemical change and a physical change? You can answer it one of two ways. You can either just answer the question, what is the primary difference between a chemical change and a physical change? Or you can give an example of each. So you can say an example of a physical change is this, example of a chemical change is this. We'll take a couple minutes for you to get your answers back. Let's say another 20, 30 seconds or so. Okay. Everyone got their ideas down? Okay, pass them to the outside of the aisles. It doesn't really matter which direction. I'll come around and grab them. I gotta make a circle anyway. Okay. Everyone feel like they know the answer? Or one of the two answers? Good. So a chemical change exhibits a change in the atoms. Or the atomic makeup, or something along those lines. There's a lot of different answers I'm going to accept here. But basically, when you have a chemical change, either the types of atom or the ratio of atoms change in the overall process. A physical change does not do that. So when water melts, beforehand, you've got water as an oxygen and two hydrogens as a solid, as ice. And then if it melts to a liquid, you still have an oxygen and two hydrogens. So there's no change in the atomic makeup here, so this would be a physical change. Melting, vaporizing, condensing, all those types of physical changes are all physical changes. Okay. Chemical change then would be something else. Like for example, iron. I think the one we use is iron plus oxygen goes to rust. Yeah, very, very easy. Most people know it. So that's a great example. Okay, questions about that? Yeah.
I have a question about example.
Okay. Yeah.
Would making a cake be a chemical change?
It would be a chemical change. The reason why is because as it cooks, the heat that's going into it is causing chemical reactions to occur. So, like the rising of the cake is actually gas being produced, and it's being trapped in there, and that's why it like expands and grows and stuff. So cooking is almost always a chemical change. If there's heat and stuff involved, there are forms of cooking that are just mixing. That would just be a physical change, but once you're actually causing something to happen, it'd be a chemical reaction.
You mentioned something in the previous class about like when you see chemistry in everyday life. You had to change your car battery.
Oh, yeah.
And you realize that, I guess, if your connectors aren't on there secure enough, what can happen is you can lose energy from the battery depending on what the humidity is outside. And it can sap the energy out of the battery, is what they were telling me.
It will,
So they
actually.
were saying keep those connectors good, and then they were talking about how like that acid build up, it's like laundry detergent gets on top of your connectors, how that can affect it and how it's corrosive. And
Yep.
so it was like triptodazone actually turned into like a cool extension of
Chemistry class. Yeah, if your battery is ever dead, one thing you can do to, as a, like a last ditch effort to try and get it to start is pour soda on the terminals, like Coke or Pepsi or whatever, and what happens is, like the Diet Coke I'm drinking here is very, very acidic, and it eats away that corrosion, and then exposes new surfaces so it makes a better contact, and then hopefully your car can start. The reason I say it's a last ditch effort is because it's not super useful. Like everything else doesn't work. I'm going to try this last thing type moment for it, but like if you wiggle them and stuff and make better connections because of the corrosion and so forth, it makes a lot of difference. As someone who drained many batteries over my life, or someone told me, I didn't actually figure it out. My old car. Have I told you about my old car yet? I use the examples in here. Oh, so when I was in college and grad school, my parents gave me their old car. It was a '76 Chevy Impala, and it was pea soup green. So this was during 2000 to 2010 time period. So it was like 25 years old and so forth. The battery in it had never been replaced, actually. So it was amazing that the battery still worked. However, the flip side of that was I drained the battery a lot. So it didn't hold up very well. So once I replaced the battery, we were in much better shape in terms of the car. Eventually, some part of the engine that's important fell out. And then they're like, yeah, don't fix it. So that was the end of the car. Okay, so that's our attendance question for today. Hopefully everyone's feeling fairly confident about that. What we're going to do today is move on in topics and talk about several different things. The first one being scientific notation. Now, I'm going to ask you guys to keep me honest in terms of the notes because of the fact I'm teaching multiple sections of this course. I don't want to skip some section thinking I already talked about it and so forth. So if you're following along the notes or something and all of a sudden I skip way ahead, or let me know. This is not that case. I've actually rearranged things a little bit so we can talk about scientific notation before we talk about the SI system and so forth. So scientific notation is really a way to write out very, very large and very, very small numbers. So last class period, we had a number on the board that was 6.02 times 10 to the 23rd. And I think maybe it was 3 times that actually, and we drew out what that number was, and you saw how long it was. Imagine if you had to write that number out 10 times. You think you'd make it through all 10 without making a mistake in it? I know I wouldn't. I barely get through 1. I've got to count them off as I'm doing it and so forth. And this is not just some random number. This is actually a really important number in chemistry, and we'll get to that later on. But it's so much easier to work with it when you write it in this form, which is called scientific notation. Now, to understand scientific notation, you have to understand a couple things. First, it's working with powers of 10. That's where this times 10 comes from. And what's nice about that is because when you multiply by 10 or divide by 10, you can just move the decimal. So if I have 6.02, and I want to multiply it by 10, I'm going to move the decimal one position this way to 60.2. Okay, so it's very easy to do in your head, multiplying and dividing by 10. If I divide by 10, 6.02 divided by 10, I'm going to move it the other direction, and it becomes 0.602. So 10 is a phenomenal number to do math with. And this is really one of the main points of the SI system as well, is the fact that the entire system is based on 10. So you can just move your decimal place however you want. Now, a lot of teachers will talk about the SI system and give a lot of words and so forth, and I think it gets kind of confusing. So let's just work a couple examples. And I think many of you have had the SI, or scientific notation, before. Has anyone never seen scientific notation? And let's just see where we stand and going forward with it. So let's take a number such as this, 345. To turn this number, which is decimal notation, into scientific notation, you have to do two things. The first thing you have to do is make the number between 1 and 10. And then, as you're doing that, you're going to count the decimal moves. So our decimal right here is where it starts. And we have two options. We can either move it to the right or the left. If I move it to the right and add a 0, I actually get further away from 10. So that's not good. So I'm going to move it one space here, and that would be 34.5, which is not between 1 and 10. Move it a second one, and that's going to be 3.45. 3.45. So it's between 1 and 10 now. And I moved it two places, so it's going to be times 10 to the second. So 3.45 times 10 to the second. And that's our scientific notation. So 3.45 times 10 to the second is equal to 345. Why don't you guys try? Let's say 1, 2, 3, 4. See if you can change 1, 2, 3, 4 into what it would be in scientific notation. So on your paper, let's take 30 seconds or so and figure that out. Okay. Anyone feeling brave and want to share what they've got?
1.234
Perfect. Okay, so it's 1.234 times 10 to the third. You moved your decimal place 3 places, so it starts here. 1, 2, 3. Exactly right. Now, throughout this course, what we're going to do is I'm going to set up problems on the board and so forth, and then give you guys a little time to work on them, and then come back and work on them up on the board to make sure everything's good and makes sense and so forth. Why do I do it this way? It's the same way as, remember at the beginning class with my juggling? I didn't juggle any. Oh, surprised I can juggle. One of the things that I always stress with students is watching me do problems on the board is not the same as you doing them yourself. And that gets students in trouble because they're in class watching things up on the board, such as doing this, and they're like, oh, that's easy, I can do that, I won't worry about that. And then when the exam comes up and they have to do it on their own, then they don't either trust themselves or they don't know how to do it or something like that. So So one of my philosophies is the fact that I actually want you guys to work these problems and try them on your own. If you get stuck, that's fine. Then we can work on it together and so forth, but then you know where you stand. So that's kind of the philosophy of it. It's the same thing as playing guitar. Honestly, I have multiple guitars at home because I really want to learn how to play guitar. But at the same time, I don't put the time in to practice it. Like, I just watch people playing guitar and I say, they make that look so easy, I could do that. And then I pick up a guitar and I can't do it. The same thing with homework and chemistry problems and so forth. You can watch me doing them up here in class and it seems very easy and so forth. You can do it on your own. But if you don't actually practice and try it yourself, then you never know if you can actually do it. So that's why we do the problems this way. However, exactly right. Perfect answer. So that's what happens when the number is larger than 1. So if the number is larger than 1 in its decimal form, your exponent here is going to be positive. So anytime you've got a positive number there, it's going to be a large number, so larger than 1. If, on the other hand, you have something like 0.0032, then in this case, instead of moving to the left, we're going to move 1, 2, 3 positions. And this is going to become 3.2 times 10. And this time we move to the left instead of the right. So it's going to be a negative 3. And we know, we can double check that that's right, the negative, because this is smaller than 1. So if you're going from decimal to scientific notation, then if you move to the right, it's negative. You move to the left, it's positive. But I always think of it this way. If it's positive, it's a bigger number than 1. If it's negative, it's a smaller number than 1. It's just how I keep track of it. Okay, so let's have you guys feel okay with this? Try more. Okay, so let's do something the opposite direction then. Let's do, let's see, 4.57 times 10 to the minus 6. So take this scientific notation and on your paper, convert it to a decimal representation. Or on your head. I don't really care if you write it down or not. Everyone got their ideas? Now I'm going to write this one up on the board because it's got a lot of zeros involved. So here, minus 6 means we're going to move it 1, 2, 3, 4, 5, 6 positions for our decimal. Then we're going to fill in zeros. So you end up with 0.0000457. So decimal, 5 zeros, 457. Everyone good with that? So I think you guys are getting the grasp of it. This is as much as we will really need in terms of this class. The only thing that I do want to stress to you that does trip people up a lot is plugging it into your calculators. So remember, for exams, you won't be allowed to have a programmable calculator or your phone or anything like that. So this is something I highly encourage you to practice ahead of time. So for example, 3.0 times 10 to the second. 3.0 times 10 to the second is actually equal to 300. So if you type that into your calculator, it should equal 300. Now, how do you type it into your calculator? Well, that's the problem. Everyone's calculators are slightly different. The general idea that you're going to do is type 3.0 and then EE. The EE button is the same as the times 10 to. And then 2. A lot of students will type this in and they'll type in 3.0 and then use the multiplication times 10 and then raise that to the second. Or even do 3.0 times 10 and then take that whole thing and raise it to the second or something, and it gets really confusing. So the button sequence that you would hit for this is actually 3.00, then the EET, and then 2. Oftentimes the EE is above the buttons, and in that case you'll have to hit a second and then EE. And this is where it gets kind of confusing. This is why I want you guys at some point in the next week to practice this so that you know that you can do it correctly. The other thing that trips people up is the negative. So if I have 1.5 times 10 to the minus 3, this is going to be equal to 0.0015. But what you need to do when you're typing this one in, it's going to be 1.5 EE, and then the plus minus key, because it's a negative exponent, and then 3. So it's 1.5 times 10 to the negative 3 as you're doing it. And when you hit equals, it should end up with 0.0015. And different calculators are different. So if you have questions or you have problems or anything, just show it to me, and I'll show you how to type it in. I don't want people missing questions because they're typing it in their calculator wrong. This is a technology class. Does that make sense? So that's scientific notation. In chemistry, we use very, very large numbers, very, very small numbers. So 6.02 times 10 to the 23rd, this is the number of atoms in what we call a mole. A mole is an amount of stuff. That's why the little picture up there is of Mr. Mole as a scientist. That's actually Avogadro the mole. He has a name. I didn't make it up. That is his name. He has a little sister called Millie the mole. So remember that in the next slide when we get to scientific notation. Or not scientific notation, but yeah, scientific. So that is a very, very large number, obviously. The size of an atom is roughly 1 times 10 to the minus 10 meters. So when you're talking about the size of an atom, that's really, really small there. We can't really imagine how small that is. I've got a graphic later on in the course that will show us relative size to it, but it's incredibly, incredibly small. So in chemistry, we deal with all matter, as we talked about before, so that's everything from very small to very, very large. The mass of a planet or something could be important. That's why we use scientific notation. Plus, just writing out all those zeros is annoying. And throughout the class, you'll learn chemists, we tend to avoid work. We don't like doing things that we don't have to do and so forth. So this is one prime example of how we simplify our lives by using the notation instead of the actual decimal numbers. We good with scientific notation? I'm moving on. Last chance? Actually, not last chance. You can ask me that. Okay. So the next thing we're going to talk about is the metric system. And the metric system is the system that is agreed upon to measure things. Now, throughout most of the world, the metric system is just used in everyday life. If you were raised anywhere in Europe, you would learn about the metric system from your first day of kindergarten all the way through. You know, if I was to measure the distance from me to the door, it would be in meters. Okay, some form of meters going across there. And you'd learn that in kindergarten. Here in the United States, however, we like to make things difficult. And we wouldn't measure it in meters, we would measure it in, well, what would we measure the distance from me to the door at? Feet? Okay, feet, or maybe yards? I don't think miles would be fine. So we have differing numbers that we use. Now, I will beg you to believe me that the metric system is easier than the English system for a variety of reasons. One of them is the fact that outside, So in the world, the red ones are the countries that still use the English system. Everyone else uses the metric system. If you look, the English system is not used in England at all, even though that's where it started from. We are one of very, very few countries that still use it. I think there are 3 or 4. There may be one missing there. But there you go. And this causes issues. So in today's world, scientists or engineers from the United States work with engineers from other parts of the world. People who are distributing food, for example. The food may be packaged here in the United States in gallons and then go to Europe and it has to be in liters. So this is issues all over the place. One horrible example of this is one of the rovers we sent to Mars. The first one, we sent it to Mars. Everything was going perfectly. It's in the Mars atmosphere. It's going down to the ground. It's getting ready to touch. And all of a sudden it accelerated and just smashed into Mars and destroyed itself. And this was like a decade ago. So scientists obviously are like, what's going on? Why did this occur? I'm sure they use different words. Let's say you spend a decade doing something, and all of a sudden, at the last moment, something goes wrong. I'm sure some choice words were used. Well, they looked into it, and what happened was this. The engineers who worked on the actual landing approach and so forth was split between engineers in America and engineers in Europe. The engineers in Europe programmed everything in meters. The engineers in the United States programmed everything in feet. So 3 meters is very, very different than 3 feet. And because of this, it crashed. Since then, we successfully have landed on Mars. We've studied Mars, all that type of stuff. So it wasn't the end of the world. However, I can't even imagine how much money and time was actually wasted on that because of that silly mistake. So it's a problem. The United States just doesn't want to change. Technically, we have been changing to the metric system since the 70s. When was the last time you saw a road sign that had metric on it? I don't know if you ever have. I see them from time to time, but mainly because I'm looking for them. They're just not out there. The U.S. doesn't want to change. We want our milk in gallons. We don't want to buy milk by the liter. For whatever reason.
Isn't there something that
2 liter is the same, except the funny thing is when you go to Europe, you don't buy 2 liters, you buy liters. They're like half. I like being smart than half. Yeah, I don't know why soft drinks are in 2 liters. It's one of the few exceptions that we normally run across. It's really hard to find soft drinks in Europe, though, in case anyone's curious. I mean, it's not impossible by any means, but it's not nearly as much as it is. Okay, so the metric system. The U.S. still uses the English system. The other thing about the metric system I would point out is the fact that it's all based on 10 and it has relatively small number of units. So whenever you're measuring length, a distance, it's always based in meters. In the English system, we have feet, we have yards, we have miles, we have, apparently there's one called rods, furlongs, leagues, I don't know what else. But there's a lot of them that we have. And they're all related to each other in different numbers. In the metric system, everything's on 10 and it's all in meters. Mass is always in grams, time is always in seconds. When you get to temperature, it gets a little bit confusing. The true metric measurement for temperature is Celsius, and that's what most of the world uses. What is our temperature measured in the United States? Fahrenheit. Fahrenheit. So there's a difference there right off the bat. You can remember that room temperature in Fahrenheit is about 20 degrees Celsius. So a nice day is about 20 degrees. If you get much higher than that, it's too warm. Much lower than that, it's kind of cold. Okay, so that's Celsius. Now, I've got Kelvin written here because scientists don't like Celsius. Remember at the beginning of class I said that chemists think of temperature as the motion of atoms? So the higher the temperature, the more motion an atom has. So if it's really warm, it's zipping around long distances and so forth. If it's cold, it's moving short distances. Well, when you think about that and you say distance is temperature, what would a negative temperature be? Well, if it's not moving at all, it would just be zero. So then how would you, there's like negative, you can't have a negative distance, right? Because if you move the opposite direction, you're still moving a distance and so forth. So what does that mean? Well, to a scientist, it really doesn't mean anything. So we use Kelvin, and that then says that there's no negatives. There's no such thing as a negative Kelvin temperature. When you get down to zero, that's when it stops completely. And that's called absolute zero. So at absolute zero, atoms would stop moving. Theoretically, I don't think we can ever get to that point. We get really close in terms of numbers and so forth, but we can't ever completely stop atoms from moving the way it is. So Kelvin exists because we don't want negative temperatures. And that's the idea there. Volume is liters. This is a little different, but it's always measured in liters. And then amount of a substance is there grayed out. We don't have to worry about it now, but later on in the term we'll talk a lot about it. When you're talking about the amount of something in the metric system, it's a mole. Okay? A mole is a number of things. So I don't want to get too much into mole now, but it's just a name for a number of things. So if you go to the store and you buy a dozen eggs, how many eggs do you get? 12. Okay? If you go to the store and you buy a pair of socks, how many socks do you get? 2. Okay, so those are just numbers associated with a name. The same thing here. A mole is a number of atoms, or a number of pencils, or anything. It's just a number of things. You can have a dozen atoms, or you can have a mole of atoms. Okay, and the chemists just work with moles as an amount. And that's in the metric system itself. So you've got relatively few systems and units. Meters, for example, is always distance, and we abbreviate meters with an M. So if you see something like 10 M, that would be 10 meters. Grams is a G, and G would be 10 grams. And you can go through all the different ones. They're just the first letters of each of them that you're going through. So it's nice to have a relatively few systems and always use the same unit when you're measuring things. But sometimes you need to talk about big differences in distances. So for example, the distance from me to the door you may measure in meters, but the distance from me to Cincinnati, you wouldn't measure in meters. Right? Because that's just a very large number. And we can simplify that down. So we use powers of 10 to do that. So you start out with a base unit, whatever that is. It doesn't matter if it's meters, grams, liters, or whatever. It sits in this position. And then you change by a factor of 10 for each step that we go. So we go 10 bigger, it's deca. 10 bigger than that would be hecto, and so forth. Now, you don't need to memorize all these by any means or anything. I do ask that you learn 3 of them. They're the ones that have the arrows next to them. So centi, milli, and kilo. Those are the main ones used in everyday life, so I want you guys to be aware of them. If I'm measuring the distance from me to Cincinnati, it would be in kilometers. It's also pronounced kilometers. I'm not sure why there's 2 pronunciations for it. But that would be the distance between them. If I was measuring the distance between my fingers here, that would be in centimeters. So it's still meters. We're just changing the unit to describe the overall distance associated with it. So if, for example, I wanted kilometers, that abbreviation is K. So that would be something like 10 km, would be 10 kilometers as you're going through it. Centi is C, so it'd be 10 centimeters as you're going through. So the unit stays the same. M is always there when you're measuring distances. The one before it changes to tell you the order of magnitude of it. Does that make sense? Yeah.
So to get the actual number, you just multiply to by whatever the number is next to, like 4 kilos, you multiply to 5,000. To get the actual number.
Okay, so for kilo, yeah. Yep, so it would be 10,000 meters. Yep. And this would be 10 times 100, okay, which I can't do in my head, but I will show you that conversion in a little while. So bear with me. We're going to, the next subject we're introducing is dimensional analysis, and that will tell us how to do story problems, which these are perfect for practicing that. So these are the three. Kilo is 1,000. So just to write these out for us all in one place. And I'll use, let's use something else. Let's use liters. 1 kiloliter is equal to 1,000 meters. 1 liter is equal to 100 centiliters. And 1 liter is equal to 1,000 milliliters. So those are the three conversions that I want you to be familiar with and use. Any other ones that come up, like on the exam, I will give you what the relationship is for that. I will also give you the relationship for anything in the English system. Even if it's inches in a foot. There's 12 inches in a foot, right? I don't work with it very often. So there you go. So I'll give it to you. Just so you guys are aware, I stole a picture of some of the English relationships. And you can see that by no means is it based on 10. They don't make any sense at all. So 1 mile is 5,280 feet. 40 rods is 1 furlong. We're in Kentucky, right? I think that's a racing. Don't horses race that far? Never mind. Okay. 3 miles is a league. That doesn't make any sense. You get all different types of things as you're going through it. There's a one called a gill. To this day, I have no idea what it means. There's a unit called a gill. I think it's a volume of liquid, but I don't know what it is at all. A ream. A ream is like what you get paper in. Why? I have no clue at all. I think there's like 144 pages in a ream. No, that can't be right. I don't know. I'm a scientist. I have no clue at all. So you've got all these different ones, and they just get confusing. So the English system I will give to you. When I was a kid, we had Trapper Keeper folders, if you're familiar with what those are. On the insides, they tried to look smart and cool by just printing all types of these relationships for you so that you could find them if you wanted them. There's hundreds of them in those things. Yeah, it's just mind-boggling how we use this system. Okay, so to review for a moment here on the metric system, you got your basic units, and it's factor of 10 changing from one to another, and out of that we've got the prefixes. The prefixes would be the kilo, milli, and centi, and so forth. And that tells us order of magnitude. So mm is going to be milli, and then meters. By the way, milli, that's where millimole comes from. Milli the mole, your girl mole. For us. Take a look at the picture. Centi is C, and then kilo is K. Hold on. It won't take too long. She wears her safety goggles to be safe. So for a chemist, moles are really, really important. And we'll get to them later, but I just wanted to introduce them to you now as we're going through it. Any questions about the metric system before we move on? And we're going to do conversions here in a minute. So, okay. Then the next thing we're going to talk about is dimensional analysis. It's got a variety of different names: dimensional analysis, unit analysis. There's a couple other ones, but I never use them, so I forget what they are. But what it really is, it's a way to solve story problems. Now, we're going to start out doing some very, very simple problems, and you can do them in your head most likely, but the point isn't to find the answer, it's the process getting to the answer. Because once we learn dimensional analysis and the steps of it, we're going to use that through the rest of the course. And later on in the course, there is definitely going to be problems you can't do in your head, so having the steps there to follow along with becomes very, very useful. So let's come up with a problem, and let's just use the metric system, for example, and say, how many millimeters are in 5 meters? So the question is, how many millimeters are in 5 meters? And many of you can probably do this again in your head. That's not the purpose behind it. The first thing that we're going to do is ask ourselves, what are we looking for? What unit are we going to have in our answer? Ideas? Millimeters. So we want to find millimeters. Number 2, what is given to start with? This is almost always the number. 5 meters. Perfect. 5 meters is our starting point. So we're starting with meters and we want to get to millimeters. The last thing we have to do is ask ourselves, do we know a relationship between number 1 and number 2? So do we know a relationship between millimeters and meters? We do. We know that 1 meter is equal to 1,000 millimeters. So if you can get through that part, ask yourself, what am I looking for, what am I starting with, and what is the relationship between the two? You're 90% done with the problem. So we have to set it up. So on one side, we're going to put what we start with. So that's going to be 5 meters. On the other side, we're going to put what we want to end with, and that's going to be millimeters. Put an equal, and then between the two goes a fraction. Now on this fraction, we've got above the line and below the line. In our relationship, we have 2 components. We've got 1 meter and we have 1,000 millimeters. So we have to decide, does 1 meter go above the line or below the line, and vice versa for the millimeters. The way that you know is that whatever unit goes on the bottom, it matches what you're starting with. So the unit there is always going to match what you're starting with. So 1 meter goes on the bottom. 1,000 millimeters goes on the top. And just the other part of it. Yeah?
Why did you put 1 meter at the bottom instead of 5?
Okay, because in our relationship here, we have 1 meter. Okay? And that's always going to be true. Don't use the 5 like you're starting with, because that is what we're starting with here. This is the relationship. So, for example, in a dozen eggs, 12 eggs equals 1 dozen. 2 pieces of bread equal 1 sandwich. It doesn't matter if you have 1,000 pieces of bread, but the relationship's still the same. Yeah.
So basically, the starting number and the bottom number, they have to be at the metric, it's not the shop.
Not just the metric system of anything. The units associated with them have to be able to cross out. Absolutely. So here, meters is a whole, it's on top. So that can cancel out with this because this is on the bottom. That leaves millimeters left. That matches what we're looking for. If it matches what you're looking for and it's the only thing left, you know you set up the problem correctly. That's why chemists, even myself and other faculty members, still use unit analysis to do problems. Not because we can't multiply 5 times 1,000, but because we want to make sure we're setting everything up correctly. And it allows us to double check. So if the only unit you've got left matches what you're looking for, then you know you've got the problem set up correctly. Then it's a matter of the math. 5 times 1,000 divided by 1 is going to be 5,000. So there are 5,000 millimeters in 5 meters. You able to follow along for now? Okay, let's try another one. Let's try an English one. How many feet are in 32.73 yards? So I'm interested to find out how many feet are in 32.73 yards. So again, we're going to do exactly the same thing. You guys are probably already tired of me saying the same things over and over, but before the end of the term, I will literally say these exact same things thousands of times to us. Well, maybe not thousands, hundreds of times. So what are we starting with? What are we looking for? We're looking for feet. What are we starting with? We're starting with 32.73 yards. Do I know the relationship between the two? Yes? Well, I know it. You may not know it. 3 feet is equal to 1 yard. I would give that to you too, by the way, because it's in the English system. 3 feet is equal to 1 yard. So I've gone through and I've answered the 3 questions. Now it's just a matter of setting it up. I use the same format. If I had like a great big stamp, I could just stamp the board with this over and over again. It will be the same all the way through. So what am I starting with? Yards, 32.73 yards. I'm ending with feet. So looking at my relationship, is 1 yard going to go above the line or below the line? Below the line? Everyone wants to fight for above the line? Okay, that's correct. 1 yard goes below the line, so yards cancel, and then 3 feet goes on top of the line. Feet matches what I'm looking for there, and it's just a matter of doing the math then. 98 point something? 98.19 feet. 98.19 feet. So that's 32.73 multiplied by 3 divided by 1 gives us that. You see how it's the same steps over and over? Constantly doing it. Okay, let's try one where you guys work it out. Let's say how many, I kind of like the English for this because you can't do it as easily in your head. How many inches, now let's do this, how many feet are in 30 inches? How many feet are in 30 inches? And I'll tell you that there are 12 inches in 1 foot. let's take a minute or two to see if we can solve and figure out how many feet we would end up with. Say 20, 30 seconds. Okay. Everyone good? You don't have your full answer down, at least you know where you're going. You can check yourself. So answering the questions, what am I looking for? I'm looking for feet. What's given to me to start with? 30 inches. And I have the relationship here. Okay, everyone good with those? Okay, so coming over here, 30 inches. I'm going to come back to that in a second. Over here, feet, and then you're saying 1 foot, 12 inches, right? Okay? So let's see if that's right or not. The way that you're going to see if that's right, we have inches here and inches here in the bottom. So those are going to cancel, and then feet matches. If it's flip-flopped, you would have inches here and feet down here. They don't match and they don't cancel. So that won't work out for you. So instead, it cancels with inches on the bottom, feet on the top, and there you go. There you go. So now, doing the math, 2.5, right? Doing the math is 30 times 1 is 30, divided by 12 is 2.5 feet. Questions about that? Now, one thing I did want to mention here is decimal places and significant figures. In terms of this class, just the lecture component, I don't care about it at all. So if you wrote 2.5, that's fine. 2.50, that's fine. All that kind of stuff. It doesn't matter. So like if you get numbers that don't work out nicely, 2 decimal places is always a good option for you to just end at. But if you want to write them all down, you can do that. Just so there you are. I don't grade for that at all, so just be aware as we're going through things that it's okay. You guys think you got a grasp of this? You want to try something a little bit more difficult? Okay. I'm not going to leave you completely in the wind here. Let's say how many... How many yards are in 273 inches? So I'll give you a minute to get started on it, and then I'll kind of give a hint, and then a little more time to work on it if you get stuck. Oh, the relationships for you that would be given to you is 1 yard is equal, 1 yard is equal to 3 feet, and 12 inches is equal to 1 foot. my hint for you to make sure that you're all in the right thing, there's going to be a way to shortcut this because you can do the math in your head. But the way that I would like to see you do it is take inches and convert to feet, and then from feet, convert to yards. So in a two-step problem in this case. Another 30 seconds or so. Everyone got their ideas? Almost fall over. What are we looking for? We're looking for yards, and what's given to us is inches. So to set this one up, as I said, it's going to be two steps. The first step is going to be going from inches to feet. And then the second step is from feet to yards. So we're going to start with 273 inches. And go to feet. So in this case, we need the relationship with inches and feet. And say that 12 inches is equal to 1 foot. I'm grabbing a calculator. Works. Divided by 12 is going to be 22.75 feet. But that's not what they're asking us for. It's asking us for yards. So I can just do another one and say that for every 3 feet, it's 1 yard. Feet cancel. 22.75 times 1 divided by 3 is going to be 7.58 yards. Is that what you guys got? Yeah, always double check my calculator skills. So this one is 2 steps. So if you don't know the relationship to go directly from what's being asked in the question, you can go through as many other steps as you want that you do know. And so you can keep track of things that way. And when you do get into multiple step ones, I find it very useful to kind of sketch out what the map would be, what the steps would be to get from one to the other. Good with that? Okay. Now the last thing that I want to talk about today is density. Now density is something that you guys have probably all talked about. Oh yeah, hey. Absolutely. Yeah. So I know some of you, I heard you guys say 36 is the conversion. If you can do it in one step and you know that conversion, then by all means, please do so. So in this course, people in here are coming from all different backgrounds. So they'll take different approaches to different problems. So as long as you get the answer right, you will always get it right. If you get the answer wrong, then I'll try and figure out what you did to get partial credit. And obviously, if I'm more familiar with it, I can give more credit because it's easier for me to figure out. But if I can figure out what you do, I'll give partial credit for it. But if the answer is right, it's always right. Assuming you didn't just copy it off your neighbor. I wouldn't know. Not that you would do that. Okay, any other questions? Okay, so density. Density is something that you talk about in just about all the different subjects of science. I think you start learning about it first grade, second grade, third grade, somewhere around there. Very easy. Why does a tree branch float? Is the classical question associated with it. But what density is, it just simply means the amount of material squeezed into a space. So if you got more material in the same space, the density is higher. If you have the same amount of material but in less space, the density is higher. So just picture in your mind atoms or things being crammed into the space. The more things that are squeezed in, the more dense something is. Now mathematically, chemistry likes it because density is a physical property for elements and compounds. So for any given element, you can measure its density and you'll see that it's always the same. So density of silver always has a certain value, density of copper always has a certain value, gold has a certain value. It really doesn't matter what it is, it's an intrinsic property of the material. So to calculate density, which they use rho here, that's actually the symbol for it, the Greek symbol rho, but most people just use D for density, is equal to mass divided by volume. Now, to help us remember that, when I was learning it, I just remembered mass divided by volume and so forth. And then I was talking to a family friend of ours, their daughter, she was like in the 5th grade or something, and she said, it's easy to remember, you just have to love density. And I said, what are you talking about? Why? Granted, I'm a scientist, so I don't know that I necessarily love density. But she says that's how she learned it. That if you draw a heart, the top of the heart makes the M, and the bottom of the heart makes the V. So that's the way she remembers it to this day. That's how I remember it. The density in the heart, and M over V for you. So if you're ever confusing, just remember that I love density, and then you've got the formula right there. You can rearrange it algebraically. So volume times density is equal to mass, or volume is equal to mass divided by density. It's fairly straightforward algebraically. Some teachers teach the triangle, and my class yesterday taught it to me. I've never actually spent time to figure it out before. Okay, so here's the triangle. Someone has to help me out. What goes here? M? M? Okay, M goes there. D must go here. And B goes there. So if you start with a triangle like this, and you cover what you're looking for, it shows you the formula. So if I'm looking for density, it's mass over volume. If I'm looking for mass, it's density times volume. If I'm looking for volume, it's mass over density. So that's how the triangle works, if you prefer that way. Again, I don't care how you get to the answer as long as you understand what you're actually doing there. And the main thing about density is the fact that it just tells you how much material is in a given space. So today, if you're taking the lab, you're going to be doing a lab based on density, and it's alchemy. And one of the easiest ways to tell whether a material is lead, silver, gold, copper, any of those types of things is just by looking at the density. Gold has an extremely high density. So, for example, are you guys familiar with the trophy for the World Cup of Soccer? Right? Some people believe that's made out of solid gold. Well, if it was made out of solid gold, it would be several hundred pounds, just because of the volume of it, and no one would ever be able to lift it over there. It's actually skinned in gold. It's plated in gold, basically, is what it actually is. Crowns are another one. Real gold crowns from like the Middle Ages and stuff would have been insanely heavy on people's heads. They wouldn't have worn them for very long at all, just because the amount of material and the density of it is so high. I think the density of gold is somewhere around like 20. So that's a lot. I know you don't have this anywhere. Oh, actually, I do have it. Yeah, it is. Gold is 19.3. So lead is about 11. So if you took the same volume of lead and changed it into gold, the mass of it would double, is the way that would work out. So for the same space or the same size crown of the two, the gold one would be twice as heavy. Versus aluminum, it would be 10 times heavier as you're going through it. Okay, so that's where we're going to end today. Please, over the weekend, spend a few minutes practicing dimensional analysis. There's a variety of different sources for you to get problems from, or just make up your own. It'll be useful later on. Okay, that's it. Enjoy your weekend, everyone. It should be fairly nice, I think. And it's a long weekend.